All right, so let's work through an example. And again, if you want to write this down, please do so. Let's find the actual displacement. So we'll need to know not the velocity function, but the position function. So if you want to pause a second and see if you can follow those rules and figure out the position function, please do so. This is what we would obtain after integrating. Again, the t goes from t to the 2, and then we divide by that new exponent. So 4 divided by 2 is 2. Here, this goes to t to the 3rd power, and then we divide by that 3. Nothing to cancel here, so it just stays at 7 over 3. And this goes to the t to the 4th power. We divide by 4, which we can cancel and say we're just dividing overall by 2. And again, add that constant term. Now we are looking for an actual value for the displacement, so we are going to go ahead and plug in values. Recall that displacement is just a comparison of where you are now versus where you started with. So we always take the later time minus the earlier time, so x of 4 minus x of 0. So we would plug those values into this function that we just created. Be careful plugging things into our calculator, and you get 53.3 for all that top one, plus that constant. And in the bottom, you just get the constant. That's why it was called x sub 0, because it's what the answer is when 0 is plugged in. And so our delta x would be 53.3 meters. The x sub 0 drops out. You'll notice that happening as we're working through this. And eventually you can just drop it out right from the start. Kind of cool then. Again, our estimates were definitely taking us in the right direction, but this is a more exact value. Right, and by the way, this is maybe a more efficient way of writing this out. So if you want to take a look at sort of how that's set up, how we would write that all out, this is something that you'll see me using in class.